All right. Good afternoon, everybody. Good afternoon. Can you hear me? How you doing?
I can hear you. Doing good.
Okay. Okay. Good. All right. So, whoa, looks like everybody's here because I keep bugging them if they don't show up. So this is a small class. I can do that. I can do that. And also let's welcome Joshua. He joined in last minute. Joshua, can you introduce yourself a little bit? A few seconds.
Oh, there we go.
Uh,
Now I got it working.
I think I was here last week, but oh,
You
sorry,
were, huh?
wrong
You were.
Joshua.
Okay.
Am
Mhm.
I?
You're a senior, right?
Yes, I'm a senior.
And then this is your last semester, isn't it?
Yes, that is also
It's
true.
okay. Well, are you aero tracks or you're designing airplane already?
Yes.
Okay. So it's kind of sort of flip-flop the process because this class is supposed to be sort of supporting the senior design process, but it's okay. So I hope you pick up something interesting and important because this class is a design of airplane, and then as long as I'm teaching this class, heavy emphasis is using software. I'm a computer geek. Unlike Dr. Ash was. He was a professor for a long, long time to teach this class. If he teaches this class, it's 100% analog class. But now I'm sort of turning lots of components into digital using software and to design airplane and sort of predicting performance at the same time kind of class. So I hope you enjoy that. Um, so everybody's here and Matthew and sorry, Joshua Hovland. Sorry about that. Joshua Hovland, you're still in California, right?
Yes, that is
Yeah, so,
true.
sorry about that. That's what I meant. Joshua Stephens, he's new.
Oh,
He joined in. And Joshua Hovland, you are my advisee. I know you since you're a freshman. And you're in California, and I hope you come back next week. Next week when you come
Yes,
back.
I'm coming back on Sunday, and
And
I'll be
also
there.
Matthew too. You're from California, right?
Yeah,
No, I'm from
no,
Michigan.
No, no,
Which
Matthew.
Matthew?
Matthew Dima.
yeah.
My bad.
I'm planning on coming back on Saturday.
Yeah, sorry about that. Yeah, it's a small class, so don't worry about it. If you get confused, just to speak up. Okay, I apologize. Okay, so hopefully next Tuesday, right? Next Tuesday we see everybody in class. Right now we have 13 students, and then class capacity is 14. So you can come in. Okay, so we are going to turn starting from next week. Everybody will be in class. Okay, now here's an important thing. Okay, even though everybody can fit into the class, okay, I'm going to continue broadcast using Microsoft Teams, just like this from the classroom. The reason is things will happen. I know. Okay, I hope you don't, but I actually tested my COVID yesterday, and I'm waiting for the results. Suppose if I'm positive, what happens? I can't go to school. I have to continue teaching online like this, you know. Uh, and if one of you got positive, you need to be isolated, so you cannot come to class. But I want to continue doing online live lecture, so that's why I'm going to use Microsoft Teams from the classroom. So suppose in one class you really cannot attend in class, you can choose to participate online from your home. Okay, just don't abuse it. In other words, don't be lazy. If you can come to class, please come to class. Or just because I feel like I want to do online today because I'm lazy. I mean, please don't do that. It is going to negatively impact against your teammates. Let's talk about teams. And also, okay, if you have any question, just to speak up. If you are very nice person, if you want to raise your hand, first of all, you can do that. I can instantly notice. Go ahead, try raising your hand right now. Okay, yeah, just like that. So if you raise your hand, I can instantly notice. But if you keep raising your hand, I kind of saying, well, hey, you keep raising your hand. By the way, Joshua, you keep raising your hand. Do you have a question, kind of? So don't forget to lower your hand, right? Uh,
Sorry
okay,
about that.
it's
Still
okay.
new to Teams.
The Dr. Running always forget lowering his hand in every meeting. So people kind of know, hey, well, Dr. Running, do you have a question, or you just keep forgetting? Usually he keeps forgetting lowering his hand. Anyways, okay. So before we begin today, let's take a look at Ernie. This is Ernie. I logged in. Are you looking at Ernie, my desktop, right? Okay, okay. Could you raise your hand? Are you looking at my desktop, Ernie? Can you see that? Okay, good, good. Appreciate. So important thing is you go to Canvas and click on this class, AE317, Flight Mechanics and Performance. And of course, my page looks different from yours because I'm instructor. I got a lot more buttons here, but just to click on people, and then of course, click on the course project. If you have a computer right in front of you now, you can actually visit this page if you want to. So this is actually one of those most important pages in Canvas. This is the project team page, okay? So click on this tab, course project under the people, okay? Go to Canvas, people, course project. I created total 5 project teams right now. And looks like team 1 is already full, maximum 3. 3 people already signed up. So team 1 is pretty much fixed. Team SAE, this is kind of special team right now. Only Jessica Mirad is the team member. I'm going to provide her a special project, which is linked to SAE Aero Connect, which I think she talked a little bit about that in last class, right, Jessica?
Yeah, I
Hello.
did.
Yeah. Do you have a plan to recruit someone, or do you want to do everything by yourself? Well, you don't have to
Well,
make a decision now, but both. Okay. So you keep your option open, right? So if any of you want to work with Jessica, I think the prerequisite for that is like you need to be a SAE member. Is that right, Jessica?
for this project, you don't need to be,
Yeah,
but
well,
ideally you join.
well, we can say that. Well, you have to be a SAE member, then you can work together with me, kind of thing. Then I'm gonna give you tons of work. Well, it's okay, but you need to talk to Jessica. You can still join. I tentatively set maximum 3 members for this Team SAE. Okay, so this one is actually funded, and I want to see what's gonna happen. This is the design, build, present, not the fry. Everything virtual. Design, build, present type of design thing. It's urban mobility project. SAE Aero Connect. Team 2, 3, 4 wide open. So we got 9 people. You can sign up on any team. Okay, you want. All right. Or you can sign up talking to Jessica and sign in. Anyways, so when will be the very first project? Let's just find out. Okay, I'm gonna go back to home page and take a look at course materials. So the very first phase of the project will coming up here. AE317 course project phase 1A, basic airfoil and wing analysis. This is not activated yet, as you can see. Okay. Once I activate, you're gonna see the type of fonts will be different. I'm going to sort of change the font type into boldface. So you can actually see, well, this is activated already. You can download the contents, but here it's not activated yet. But as soon as I activate, I'm going to announce it, and then you can see the document of course project phase 1A. This is going to be the very first phase of your semester project. Total, I think 4 phases, 1A, 1B, 1A, 1B, 2, 3, and 4. 4 is phase 4 is a final presentation, project final. Project final is going to replace the final exam. This class, there's no final exam, but instead, you are going to do a final project presentation, okay? During the scheduled final exam time slot, you're going to do a team presentation. It's called final presentation, FP. That's the phase 4, okay? So I haven't really finalized it yet. I'm still thinking and developing the instructions document, but the first phase is going to coming up soon. So before this happens, you probably need to make up your mind and make up your own team or join a team. You can freely join yourself to any team, okay? I'm not going to force you to do anything. You make your own decision. You create your own team. Now, suppose if you don't like your team, you can change your team. That's fine for each phase. No problem. I don't care. So before I announce the first phase, phase 1A, I'm going to basically announce it so that now is the time you have to sign up for the team. If I do not see your name as a part of one of those one of those teams, okay, you're not going to do phase 1A. Okay, I'm going to announce it. Not now, but it's going to come fairly soon. Once you sign up, each team, I'm going to create, like I said, 2 OneDrive file folders. One is for submission. The other one is graded work. So each phase, I'm going to do that. So you can switch back and forth for different teams. That's fine. I don't care. So I'm going to basically create the 2 OneDrive file folders for each team, 2 of them, okay? So that you can actually share the files using OneDrive among those teammates. And also final product, which is probably usually report for each phase, or could be a presentation slide for each phase. I don't know. You are going to submit also into the OneDrive file folder submissions for each team. Do you have any question? I hope it's clear. Okay. All right. Let's double check. Okay, if you understood clearly, please raise your hand. This is right after lunch, so I kind of suspect that some of you might be sleeping, you know. Please raise your hand. All right, good, thank you. So let's move on. Okay, so that's the team formation, okay. So today, let's just get into Unit A1, you know, today's the first day of lecture. This is airplane flight mechanics and performance, okay. Dr. Jeff Ashworth, who retired last year, he is the one, you know, he's the one actually created the entire contents of this class, and he's the one teaching for long time. And then it was very interesting class. If you love airplane, man, this is cool kind of class. Lots of things we cover for airplane design, airplane, you know, small details of airplanes. Very maniac. If you enjoy those things, then you're an airplane person. Nothing wrong for that. I do love airplanes. You know, I'm interested in lots of details. I oftentimes visit like an airplane museum. Actually, 3 weeks ago, I went to Ohio. I visited U.S. Air Force Museum. This is like 3rd time visiting with my son. We spent about 9 hours just walking around like 5 hangars. There was not enough time for look at every airplane. It took like, I don't know, a few hundred pictures. And then they opened up some of those airplanes, and then they invite people walk in and touch it. And then, you know, there's actual crew who flew that airplane showed up and then explain and tell the stories, and lots of fun time. Museum was open until 9 p.m. We stayed until 9. So anyways, airplane. such a wonderful thing, And then right now it's a winter time for AEs. I guess you know that. Airplane industry is cutting people. Boeing is struggling. Just about big companies, U.S., military section, you know, civil section, both struggling to hire new people. It's because of COVID. People just don't travel, don't take airplanes, and then demand is going down. Now, okay. So if you want to chat, just go ahead, do it freely. Okay, this is a small class. Okay. Now, I kind of look back when I was a student. Wait a second. I went through similar things a few times. When I was a grad student at Kansas, I went to Wichita State University, which is a kind of unique school because half of that population of that small city of Wichita, Kansas, are employed in aerospace industry. They have Boeing uh, factory there, and then they have like a Bombardier, and they have Raytheon, they have Beechcraft, they have Learjet, they have Airbus, and there are lots of airplane industry is clustered in that small city, Wichita, Kansas. And then there are fluctuations. Sometimes economy is not doing well due to many reasons. And then what they do is they basically give employees an opportunity to leave for a moment and go back to school. And then all of a sudden, the graduate program of that school is filled up with employees of Boeing and Airbus and Beechcraft and Raytheon. Everybody is working at some company locally, and then I'm the only guy, like a regular kind of student. I experienced that kind of situation. And then one thing I have to emphasize, since you chose this major, AE, okay, you probably shouldn't assume that, hey, education at Embry-Riddle is my terminal education. You shouldn't. Company is going to probably encourage you to go up higher degrees. They even pay for it. Boeing actually have a program, internal program that actually pay tuition all the way to the PhD. And then in the past, some of the students who graduated from my research lab, all of them at least got master's program. I got like 3 students got PhD. 2 of them actually paid by their own company. Okay, so do not think that, hey, the current situation is miserable, but that's not what you're seeing in the future. Okay, so don't be discouraged, but I would like to motivate you. So this kind of class is quite important because I'm going to share some nifty things. Okay, let's find out small tiny gadgets, small tiny details of, okay, I know how to use this software. This is a free software, open source, developed by MIT professor. There's absolutely no manual of any kind. In order to use it and make it work, you really need to know the heck of details that no one else knows. Okay, so that kind of class. So I want to kind of try to keep you motivated, stay focused, and then enjoy your project. Okay, if the project doesn't pan out well, that's fine. I mean, if you discover tons of things, that's all it matters. So anyways, having said that, anything you want to say? Um, don't hesitate. We got small class. Did I actually record? Oh yeah, I'm recording. That's why. Actually, since I'm recording, we cannot argue, oh, you didn't say it, or oh, no, I said it kind of argument, because everything's recorded. Too bad. But don't worry about it. If you want to say something, go ahead, say something, okay? Or if you want to raise your hand before you say something, that's fine too. Okay. So let's begin Unit A. Okay. Overview of Unit A. Unit A is aerodynamics and airfoils. So if you took especially my aero class, this is almost like a repeat of the same thing. Okay. But it's a good time to review what we learned from aerodynamics because every airplane design starts with aero. So if you do poor job in that stage, that's it. Your airplane sucks. No matter what you do after that. So keep that in mind. You need to have at least one really, really, really good aero person in your design team. Otherwise, your airplane sucks no matter what you do. Okay, so let's begin. So Unit A, I'm going to cover two subjects. One is a fundamentals review, okay? The other one is characteristics of airfoil to begin with. So I'm going to cover the how 2D cross section of a wing called airfoil actually make a big impact on overall design to begin with. Okay, so today, okay, I'm gonna go all the way back to actually fluid mechanics once again. Let's take a look at some of the fundamental equations, something called continuity equation. Continuity equation coming from conservation mass principle and then Reynolds transport theorem. I hope you remember those from fluid mechanics. And also, I'm going to talk about Euler's equation, and then Euler's equation, of course, under certain assumptions. We can develop Bernoulli's equation, which is pretty useful, and then pretty much that's the only equation we can use if you want to have some hand solution. Euler's equation is not your tool, right? Euler's equation is not your tool, right? Do you agree? If you stay quiet, I may end up only give you Euler's equation for exams. Do you want that? Why Euler's equation is not useful? I don't want it. Somebody please tell me. Some basic questions like that will be very important. When you try to do a job interview, probably people will ask that kind of question. You need to get used to it. Why? Okay, so I give you either Euler's equation or Bernoulli's equation. Which equation do you want? Go ahead. You don't have to raise your hand.
Oh, okay. Yeah, let's get both if possible.
That's fine. So just your Stephens. Go ahead.
Yeah, I was gonna say let's get both of them if possible.
One of them is totally useless. In other words, if I give you Euler's equation, you try to use it. Can you use it? Use means can you plug in the number and get the number out?
No, you can't,
No.
because it's a differential equation.
That's right. That's a differential equation. That's the bottom line. So it's a very important point, David. Of course, we start from Euler's equation, but you have to actually derive the equation from Euler's. That derive is important thing. In other words, you have to derive algebraic form of equation called Bernoulli starting from Euler's. Then derivation process actually comes in certain assumptions and limitations. Assumptions are limitations. If you make this kind of assumption, if that assumption is not kept or if it's violated, you cannot use that equation. If you go ahead still use it, what does Dr. H will do? I mean, Dr. H will be viciously grade your work and give you only 2 out of 10, something like that. Okay, so hope it doesn't happen in this class. It probably happened a lot in aero. I try not to do that, but hope you don't repeat the same thing. So today's subject, continuity equation, Euler's and Bernoulli's equation, airspeed indicators. By the way, airspeed indicator equation, do you know where does that come from? What's the equation that, oops, sorry. turn on. Okay. So one thing. So airspeed indicator. There's something called airspeed equation. Where does that come from?
From Bernoulli's equation.
Airspeed indicator equation. Something called airspeed equation. Have you ever heard of it? From Aero? In other words, somebody need to determine airplane's airspeed. Where does that equation come from?
Well, it isn't the airspeed equation from Bernoulli's equation.
That's right. It's essentially Bernoulli's. So Bernoulli's equation is going to be directly applied to come up with airspeed equation. We are going to take a look at those things. Of course, you know already, I hope. Okay. So let's just move on. So let's begin with go all the way back to fluid mechanics. Of course, we are going to apply conservation mass principle to begin with, conservation mass, but simplified to continuity equation. Okay. So if you analyze airplane aerodynamics, almost always you have to limit yourself very narrow. The very first limitation of your hand analysis is, of course, steady flow. If the flow field is not steady, it's very chaotic, random, and it's very difficult to at least express using some simple equation. And then the details are a lot more complicated. So if you want more details, I guess you need a more resolution of your analysis. And that usually is the large scale computer simulation to analyze the small tiny details of the flow field. And usually that detail is not important. Flow is almost steady. Then you can do some very simple hand calculation such as continuity equation, Bernoulli's equation. Everything is based on this constraint, steady state. So this is a big constraint. In other words, aerodynamics is massively complicated. However, if you want to somehow analyze certain things, this is probably almost always required. So your analysis is fairly limited. In other words, you can only analyze certain very simple, smooth flow field. Okay. So this is the steady flow. Okay. Now, if the flow field is steady, what is the benefit? Do you remember from aerodynamics? What's the biggest benefit of the steady flow?
Well, there's no time dependence, so your
That's right.
equations are the same no matter when you're looking at it.
Uh-huh. Even before you start using equations, what is the biggest benefit of steady flow? Some very conceptual questions. You can define streamlines. Streamlines can be defined only if the flow field is steady. If the flow field is not steady, there's no such a thing called streamlines you can define in the flow field. What is the streamline? Oh, this is a job interview. I'm an interviewer. Okay, well, I heard that you are aero truck individual graduate, and then you want to get a job from our company. This is my question. What is the streamline? I'm not kidding, okay? One of my students actually got this question, and he reported back to me after that job interview. Go ahead.
Streamline is the path that a single particle would take, right?
That's actually path line.
Okay.
Yeah. Yeah, actually, I appreciate your wrong answer too. It's a path line. Okay, so basically what he said was the great crystal clear definition of path line. Okay, anybody else?
A streamline is tangent to the flow field.
Physically speaking, that's correct. So this is, I hope you are not looking at the notes. Okay, where is it? Where is it? Did I say that? Tangent. Is the note say something like that? I don't know. Anyways,
First bullet point.
First bullet point. Every point along its length, the local velocity vector is tangent to it. What does that mean? That means suppose if you choose this path, if you take any location, velocity direction is tangent to the path. Velocity direction is tangent to the path. I don't know the magnitude, but I know at least the direction of the velocity, which is tangent to the path. That's a very good definition, physically speaking. Also, another definition is quite important. I'm going to change the color here. It is a streamline is what? Streamline is, okay, it's not saying. Streamline is actually purely mathematical concept. This is actually most important out of all definitions. That's the streamline. So streamline is actually you can basically say that it's physical. In other words, you can visualize the flow field because this is the line specifying the tangential direction of a velocity field which is present in the flow field. And also at the same time, you can visualize by injecting the smoke particles into the flow field. That particle takes the path, it's called path line. If you continuously injecting the particle in the same location, the numbers of particles follow one after another that actually create the streak. It's called the streak line. That's essentially smoke wind tunnel. What it does is, okay? So it's a flow visualization, something physical at the same time. It's a purely mathematical too. In other words, that's why you can now develop an equation in a flow field. Without this streamline concept, you have zero equation available for fluid mechanics. In other words, wind tunnel and flow base is the only way to analyze the flow field back in all days, right, brothers? Okay, so you have to realize importance of mathematical concept nature of streamline. So having said that, did I mention streak line? Where is it? Yeah, okay, streak line. Streak line is essentially a path line is a single particle's path. Streak line is this is the path of multiple particles released at the same location, and just one particle following one after another ended up having line over a streak. Okay, essentially, I'm using the digital ink. This is a streak of small tiny dots, right? But it looks like a continuous line. It's called streak line. Okay, so a streak of ink, for example. Okay, now because of well, thank God we have streamline. That's why we can apply equation. Okay, so let's move on. So there are a few equations we developed back in old days, fluid mechanics. One of them is continuity equation, or this is coming all the way from conservation of mass. Do you remember the original governing equation? Conservation of mass. So just because continuity equation is given here, this is not the governing equation. This is like a simplified equation coming all the way from governing equation of conservation mass. So you had to apply tons of assumptions or simplification constraints to simplify the equation. So this is something called continuity equation. But if you pick it up as it is and plug and chug, sometimes you are in big trouble. Because this equation is so specific. There are lots of constraints attached to it. So could somebody actually point out, okay, well, this is the governing equation, the where it's this equation coming from? Well, let's go back to the home page. Okay, so this is AE317 course materials. Oftentimes, you probably want to go back to either fluid mechanics or aerodynamics. Okay, so now my question is, where did you get this equation? Somebody please
Reynolds
point me.
transport theorem.
Okay, so which one? Let's take a look at somewhere. So you want to go all the way back to fluids, or you want to take a look at the arrow? Either way is fine. I think
I think it was unit D.
of a fluid or unit A of arrow. Either way, it's the same thing. But let's take a look at arrow unit A3. Okay. So especially for those who didn't take my arrow class, this is a good time to look at where you can find stuff in aerodynamics notes. So if you go back to aerodynamics note unit A3, so this is continuity principle, page 1 of unit A3 note, continuity principle. Okay, so take a close look at it. So this is the original governing equation of fluid mechanics. Okay, this is the same equation. It's just a different style. This is the Manson Yango Kishi, Iowa State University mechanical professor style of equation. This is John D. Anderson, professor of University of Maryland style of equation. By the way, Professor John D. Anderson is a god of aerodynamics. No one can go against him. He's the one pretty much make the rule of aerodynamics in this country. So this is the governing equation, continuity. Okay. So this governing equation basically includes everything. This portion is a time rate of change of mass within the control volume if you define the control volume in the flow field. Let's say if this is a control volume. Okay. If you define the control volume, you're going to define control surface. That's the surface where you allow the fluid flow through it. Control surface. In this case, control surface, 2 of them. Okay. So that is actually right-hand side. So this is the how much flux of mass flows through those 2 control surfaces. Those 2 added together must be equal to 0 is called continuity principle or governing equation of continuity. Do you remember those things? I hope. So let's just go back here. So how did you get this equation? Okay, that's important. So you are going to basically define a streamline in the flow field, just like that. Then at the same time, you can actually create a tube using streamline. It's called stream tube. It's a tube created by streamline. Similar to this thing. This is a stream tube. It's a tube created by streamline. So because of the definition of the streamline, velocity is always tangent to the line of, it's called streamline. So there's no flow go across it. There's no flow go across it. So this is a solid wall, acting like a solid wall. There's no flow go across it. The only surface that actually allows the flow comes in, goes out, are those control surfaces, okay? Now you are going to apply the equation here. Then come up with that equation of continuity. So what are those assumptions? We have to probably list all of those assumptions for this equation. Okay, so what is the very first assumption for this equation coming all the way from conservation mass governing equation? Anybody?
Steady flow.
Steady flow. Yes, exactly. That's what I wanted to hear. Second assumption. By the way, steady flow is completely dropping off this term, right? This is zero steady. Okay, so what's next?
Incompressible.
Incompressible is not in here, actually. Yeah,
Inviscid.
incompressible, little too fast, little too early. It's gonna show up, but not here.
Inviscid?
Inviscid is little too, well, inviscid has actually nothing to do with continuity, isn't it? Viscosity is not in the picture in continuity. Viscosity will show up in some other equation, but not here.
You have to assume that both your mass flow rates are equal. So mass in is equal to mass out.
So that's right. So you are basically assuming that, stream tube typically means that the single input, single output tube, right? So let's assume that way. So it's let's say stream tube. In other words, if the flow is steady, you can define streamlines. Then you're going to now using the streamline to create the tube called stream tube. Now you say it's a tube, so typically pipe flow, right? Single in, single out, maybe. You can actually apply this equation for multiple in, multiple out, but again, if you add all the mass flow rate in and all the mass flow rate out, it should be equal to each other. It's essentially the similar equation you can come up with. But if it's single in, single out, suppose if one is in, two is out, mass flow rate is constant. So those are the constraints, okay, to come up with those two equations. One is called mass flow rate, the other one is continuity equation. In other words, continuity equation basically says that the mass flow rate is constant if it's steady flow, okay? So let's take a look at the very simple exercise here, okay? You're gonna probably rough at it, but here's the catch, okay? I'm planning the very first quiz, not the homework. Homework is gonna come up later, but I'm thinking of very first quiz, just the very first stumbling block to challenge you off of this example problem. So just to pay attention. And also, I hope you have a calculator because I don't want to calculate by myself. So I'm going to wait until your calculation result. Okay. So example A11, next page. Okay. So this is, again, stream tube, and then let's assume this is something called one-dimensional flow. One-dimensional stream tube. That means across this station one cross section here, pressure, temperature, density, and velocity are all constant across this cross section station one. That's called 1D. Okay. And also pressure, temperature, density, and velocity are all constant across this section two. Okay, cross section here, it's 1D. Okay, so this is one-dimensional stream tube. However, pressure, temperature, density, velocity might be different between station 1 and station 2. Okay. So let's take a look. Air flows through a tube that changes cross-sectional area in a way that is similar to the tube illustrated in this figure, figure 3.3. At a point in the tube, station 1, where the cross-sectional area is 1 meter square, the air density is 1.2 kilogram per cubic meters, and the flow velocity magnitude is 120 meter per second. At another point in the tube, which is station 2 right here, the cross-sectional area is 0.5 meters square and the air density has decreased to 1.0 kilogram per cubic meters. What is the mass flow rate through the tube and what is the flow velocity magnitude at station 2? Let's just take a look at it. So what equation do you want to pick it up?
Continuity.
Which one?
The
Equation
3.2.
3.2. Okay, let's pick up equation 3.2. Okay. So equation 3.2 basically says that rho 1, A1, B1. By the way, B1, this is magnitude, okay? Let me zoom in a little bit more. Okay. So density, cross-section area, velocity at station 1 multiplied together, this is actually mass flow rate. Mass flow rate never change between station 1 and 2. That's what equation 3.1 says. Equation 3.1 says mass flow rate. It's constant. So if you apply between station 1 and 2, this is the equation 3.2. So rho 1 A1 B1 is equal to rho 2 A2 B2. Once again, velocity magnitude B1 and B2. So what do we know? Rho 1, density 1 is 1.2 kilogram per cubic meters. Cross-section area A1 is 1 meter square. Velocity B1 is, what is velocity B1? Is velocity B1. Do we know that? 120? Oh. Okay. Density rho 2. Rho 2 is given 1 kilogram per cubic meters. Cross-section area A2. 0.5, huh? Okay. B2, what is it? Okay. So obviously you're going to apply this. First of all, let's find out mass flow rate, which must be constant. Which means m over dot 1, which is rho 1 A1 V1. M over the 2, this is mass flow rate, rho 2 A2 V2. So basically equation 3.2 says mass flow rate M1, mass flow rate M.2 is essentially the same thing. Okay, so you can either use the condition of station 1 or condition of station 2 to determine, first of all, mass flow rate. Actually, let's use the condition for station 1. So using condition of station 1, mass flow rate m over dot is rho 1 is 1.2 kilogram per cubic meters. Cross-section area 1 is 1 meter square. Multiplied by B1 is 120 meter per second. Somebody please calculate. What is the mass flow rate? Okay, thank you, sir. Thank you so much. 144. Okay, can you confirm? If you confirm, please raise your hand. Confirm, confirm. Good, good, good. Okay, okay, good, good. Looking good. So this is, what's the unit?
Kilograms per second.
Kilograms per second. That's right. So how much mass is flowing for a given time? Okay. So this is a mass flow rate, which is constant between station 1 and station 2. Okay. Second question, what is the velocity B2? Now, obviously, you're going to pick up the equation from here. Let me change it. So you're going to pick up the equation from here. Then you're going to apply it. So B2 is equal to B1 multiplied by the ratio of the density, rho 1, rho 2, multiplied by the ratio of the cross-section area, A1, A2. So if B1 is 120 meter per second, density is wait a minute. That's a dumb thing to do. Let's not do this. Okay, that's a pretty dumb thing to do. Okay, so this is, by the way, rho 1, A1, B1 divided by rho 2, A2. Since this whole thing, numerator is essentially m over dot, right? So let's use the value here. Okay. So I'm going to pick up this value and plug right in here, 144 kilogram per second. And density rho 2 is given 1 kilogram per cubic meters multiplied by the cross-section area, 0.5 meter square. What is B2? Anybody?
It's 288 kilograms per second.
288. 288. What's the unit?
Kilograms per second.
No. Eh?
Sorry, meters per second.
Meter per second. Be careful. Okay, so this is B2. Great. Okay, so let me just save it for a moment. So okay, so this is the example A11, right? Are you happy? How's your response? Well, wait a minute, Dr. H, you're joking. This is a piece of cake, way too easy. Is that how you're feeling? Yeah. So I'll give you quiz 1, released probably today, maybe tomorrow, I don't know. As soon as I'm ready, I'm going to release you quiz 1, which is take home. Requires this information, okay? And then it's gonna make you think, okay? Then if you're fundamentally doing wrong thing, I will viciously grade. So keep that in mind. In other words, this is a challenge for you. Do you really understand the meaning of equation? Meaning of equation is what's the origin of each equation? Where does that come from? Okay. Now, the origin of equation is typically this kind of equation. Where is it? Arrow. Okay. Oh, this kind of equation. This is the origin of equation. What kind of equation is that? This is the integral form of differential equation. In other words, you are going to come up with this equation by integrating the differential form of the equation given. That's the origin of almost always the conservation of mass and momentum energy type of equation in aero and the fluid mechanics are all originated from differential equation. Think about it is, we are dealing with small tiny particles of air and fluid always. And then if you try to develop the equation that can be applied for that small tiny particle, and each one of them is governed by differential equation. Now, if you want to come up with the overall behavior by defining control volume in space, such as in this case, your equation, the nature was, it's going to be integral equation, right? So that's the origin. And then now you're going to further simplify. You come up with the equation you can pick up and plug and chug. Now, sometimes people just to pick up this equation casually plug and chug without thinking that process. Process actually starts all the way from this governing equation. Okay. Skipping that process just to picking up and plug and chug is a big no-no in fluid and aero, mainly because those equations are not universally applicable. Each case equation comes with different shape, right? So your ability to recognize that is crucial. If you cannot do such a thing, I guess you end up having a job on the manual labor type of job in aerospace industry, because that's the only good for you. Okay, so you have to have an ability to think through what is the origin of this equation, what is the physics associated with, what is the constraints. If I need to derive this equation, can I do that? Go all the way back to the Reynolds transport theorem. Starting from there, can I get this equation derived? That is the serious question you have to ask once again. Okay, so quiz 1. Okay, anyways, let's move on. If you feel uncomfortable, just to speak up, and you know, this is right after lunch, right? So if you're sleeping, I guess you know that's a very expensive lunch. Okay, so I'm gonna move on to next page, page 4. Euler's and Bernoulli's equations. Okay, so we already discussed about a little bit, right? Euler's equation. This is fundamentally non-useful as a tool. In other words, can I pick up Euler's equation, plug in this pressure value? Can I get the velocity out? No, you can never do such a thing. This is a differential form of equation. Okay. So problem. Can I use differential equation to solve problem? Your answer is kinda. But how would you do that? Differential equation. Starting from differential equation. What do you need to do to get algebraic equation? The equation that you really, really need, because algebraic equation is the, well, that's the friend. I can use algebraic equation. I can plug in the value. I can get actual value back. That's what engineers do. What do you need starting from differential equation to get algebraic equation?
Assumptions?
No, mathematically speaking. Assumptions are to simplify. Euler's equation cannot be simplified. You have to change the form into algebraic equation. How can
You
you
need
do
to
such?
integrate it.
Integrate.
Integrate it.
Yes, that's right. I think you knew it. So integration is always in the process, okay? Because this is differential equation. So origin of this Euler's equation is, of course, you are going to apply the physical principle to a small, tiny, single particle of air moving along the streamline. Okay, so this is it. Then the result you're gonna get is, of course, differential equation, because it's so small, tiny thing. And then you can use that equation only for this one particle within the flow field. How useful is that? None. So you have to somehow integrate the effect of this equation. Then you can come up with algebraic equation, which is happen to be Bernoulli. Okay. So let's just remember, you know, in aerodynamics, we derived Euler's equation. And also back in fluid mechanics days, we did the same thing. But Euler's equation in aerodynamics, we picked up a single particle, which happened to be a cubic element of a small, tiny portion of air, which is moving steadily along this path called the streamline. Like I said, streamline is a pure mathematical concept. So that actually helps. So you're going to apply something, a principle, or I don't know, conservation, blah, 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 to this particle to come up with Euler's equation. What did you apply? What kind of concept or blah, blah, blah law or something to get Euler's equation? Anybody? Please jump right in. In other words, what's the overall source or origin of Euler's? Where does that come from?
Would that be conservation of energy, sir?
No.
Newton's second law.
Newton's second law is correct, but is that the conservation of what? Not energy.
Momentum then?
Momentum. Yeah, that's right. That's right. Conservation of momentum. The Newton's second law of motion, aka not in the shell, is F equal to ma, right? This is a Newton's second law of motion. Conservation of linear momentum. Okay, so this is the only equation you learned from dynamics. Dr. Wald's dynamics surprisingly teaches only one thing: F equal to ma. That's it. That's conservation of linear momentum. So you apply this to this single particle moving along this streamline. Then you come up with Euler's equation. I think we did that in Aero. Okay, do you remember that? Let's just try to find out. Where is here we go. This is a momentum principle in aerodynamics. So do you remember this single tiny element moving around the streamline? You applied F equal to ma, simplify it, get Euler's equation right here. So Euler's equation in aerodynamics, once again, take a look at it. Euler's equation is an ordinary differential equation which is independent to x and y and z. Ordinary means that this equation depends only in the direction tangent to the path called the streamline. Okay. Now, if you want to apply Euler's equation in Cartesian x and y and z, what kind of equation you ended up having? I mean, it's one of those homework assignments in aerodynamics. Do you remember those? Okay. Give me three. Okay, well, give me Euler's equation in x and y, z. This is Euler's equation along a streamline, direction tangent to the path. So how about Euler's? Somebody please jump right in. Euler's in x and y and z Cartesian coordinate system. Do you remember that?
For x, it would be dp over dx is equal to negative rho times u times dv dx.
Ah, cool. du dx, right?
Oh, sorry.
Okay, yeah, that's okay. This is x direction. Y direction is dp dy is negative rho b db dy. Z direction is dp dz is negative rho w dw dz. Remember, velocity is a vector. X direction component u, y direction component b, z direction component w. So this is the definition of velocity as a vector, and then each direction x, y, z, you can define Euler's equation. Now you can notice this is a partial derivative, right? Partial derivative. This is ordinary derivative. Why is that? Why is that? Why is that? You have to understand. Those are the concepts. Okay. If you don't know those concepts, every single detail, it doesn't matter. If you understand the concept, every single small details, just you can pick up anytime. Okay, so that's the value of education. So don't miss those things. Okay, as you take this class, aero class, fluid mechanics, don't miss those important concepts. Otherwise, you're wasting everything down the drain. You're paying a lot of money to come to this school. Don't miss those. So a partial derivative means that, okay, in the 3D Cartesian space, pressure, velocity depends on the direction. So only the component in x direction is going to be differentiated. That's why. But this is the case that, okay, equation developed along this special case. In other words, this particle is moving along this path. Thank God we defined the streamline because this is a steady flow. Okay, so velocity is always in tangential direction, right? So this is a pressure change and then velocity change in tangential direction only. That's why we can handle this as an ordinary derivative. In other words, velocity and pressure only changes in the direction tangent to the path. So that's why this is simplified. Well, I would say generic Euler's equation. You can apply this as long as you define a streamline in the flow field. Okay. So don't miss those important concepts. So this is Euler's equation you developed in aerodynamics. Okay. Do you remember that? I hope. So again, this equation is constrained. What's the constraint? You have to have streamline. So when you apply this equation, you need to show me always which streamline you are applying this equation with. Otherwise, I'm not going to give you any much partial credit because you don't know what you're doing. So this equation is constrained. Application-wise, you have to show the streamline, exactly which streamline you are applying this equation with. Okay, so having said that, do you remember Bernoulli's equation? How did you get that in there? How did you get that from Euler's?
All you have to do is integrate both sides.
That's right.
Yeah.
Integration is taking place. Now, integration, in order to integrate, of course, you're going to develop streamline. And then along the path of the streamline, this is location 1. This is the location 2. You're going to integrate between location 1 and location 2, this equation. Here we go. That's what we're doing here. So this is a streamline. So those 2 points, 1 and 2, need to belong in the same streamline. Otherwise, you can never use this Bernoulli's equation. Be careful. So suppose this is a flow field. Okay. Cross section of a wing. This is a flow. This is location 1. This is location 2. This is location 3. So Bernoulli's equation is correct because location 1 and 2 belong to the same streamline, but can you do this kind of thing? Oh, P1 plus 1/2 rho B1 square is actually equal to also P3 plus 1/2 rho B3 square. Can you do this?
No.
No. What's the problem? Something's completely missing. Suppose if you add one more assumption for this Bernoulli's equation, you can actually do this. What is that one more assumption? Do you remember that from Aero?
If all your streamlines come from the same point out at infinity, then you can do that.
That's one thing. Yeah. Okay. So in other words, it's kind of hard to illustrate, but suppose, okay, that's one thing. Suppose if this is the streamline, in other words, it's originated from free stream. Free stream, you know, what is the free stream? Free stream is the term developed in wind tunnel testing. So here is infinity, free stream. And let's say this is location 1, location 2, location 3. Oh, no, you can't still do this. But between infinity to 1, between infinity to 3, infinity is infinity. So you can apply Bernoulli. Okay? But not directly 1 to 3. Okay? Also, another thing is, do you remember the irrotational flow field? Del cross B is 0. If the flow field is irrotational, completely irrotational, which is ideal flow, you can do this. Do you remember that? I made you do flow over circular cylinder in aerodynamics, right? That's irrotational flow field. Just about anywhere in the flow field, this equation applies. That's irrotational flow field. And anyways, Okay, so those are the things that you really, really need to go back to aerodynamics. Okay, so just don't forget the core concept. So here is, whoa, before you go, okay. So before you go to that, before I develop a quiz 1 problem, okay, my avatar Arnie shows up. This is not me, okay? This is my avatar. Okay. 5 more minutes. Arnie thinks. Okay, it's not me saying, okay, it's Ernie, my avatar says. Don't trust him or don't trust him, it's up to you. Do you trust him? I don't know. Ernie thinks. Okay. I can determine P2 if P1 is given. Let's just go back once again to this example A11 before you go today. It's going to be like I'm going to create the quiz 1, okay? So example A11, we spent some time today in class. We applied the conservation of mass or continuity principle to determine two things. One is a mass flow rate. The other one is velocity at station 2. So now we know velocity at station 1, 120 meters per second. Velocity at station 2 is 288 meters per second. It's fairly accelerated, okay? And then we are given density at the station 1 at 1.2 kilogram per cubic meters. Density at station 2 is 1 kilogram per cubic meters. Now Ernie thinks, if P1 is 1 ATM, standard sea level, you guys know that. It's 101 kilopascal, right? Or 14.7 psi, either way. If P1 is 1 ATM, what's P2? Then Arnie thinks, well, P1 plus 1/2 rho 1 V1 square is equal to P2 plus 1/2 rho 2 P2 square. So what the heck is P2? P2 is equal to P1 plus 1/2 rho 1 V1 square minus 1/2 rho 2 P2 square. So if you plug in 101, Arnie is careful, this is unit Newton. 101 kilopascal plus 1/2. Rho 1 is, what's rho 1? Rho 1, 1.2. Oh, okay. 1.2 kilogram cubic meter. P1 is 120 meter per second. This thing square, Arnie must be very careful. 1 minus 1 kilogram. 288, that's what we got. B2 is 288. Okay, 288 meters per second. Okay, that's right. So that's what it is. Kilopascal. What do you think? That's what the Ernie says, not the Dr. H says. Do you agree?
No.
Why not?
You forgot to check incompressible flow.
So Dr. H is going to announce quiz 1. It's basically this question, okay? Let's find out pressure P2 if the P1 is 1 ATM. That's going to be a quiz 1. I hope you can handle. Ernie did this way. Ernie bird. this way. You can trust them or you can disagree. Either way. Okay. So any other question here? We are running out of time today. So let's just stop here today. Any question? Oh, what's this text? Okay, so that's Jordan. Jordan, you still don't have a microphone, yeah? That's okay. I hope you can fix it. Any question? Last minute question.
I have a question.
Go ahead.
So, when we go back to in-person classes, are we going to be having everyone show up in person every day, or
Every
do
day,
the half and half?
No, every class. In other words,
Okay.
we don't have to split in blue and red, half and half. That's what the half and half is. We are small enough. We are small enough class so that everybody can fit in classroom with a safe COVID distance. Okay. So starting from next week, everybody Tuesday and Thursday both, everybody show up in class, and then I do lecture in class. But at the same time, I'm going to broadcast that in-class lecture through Microsoft Teams. So if you want to instead join in online, you can do it anytime. That's what it is. And then I'm going to capture every class videotaped. Does it make sense? So classroom is usually everybody in class, maybe 1 or 2 person join in online, but it's a kind of mix. But it's in class every lecture, okay? Unless I become sick. I hope it makes sense. Any other last minute question? Have a wonderful day. I'm going to announce you quiz 1, so just wait for me, okay? And then see you guys back next week. Everybody should be in class, okay? You can choose to go for online, but just please let me know, okay?
All right. Thank you.
Thanks.
Thank you.
Yep. See ya. Have a
Actually,
great weekend.
really quick, one question.
Yeah, go ahead.
When is quiz 1 due again?
Quiz 1 due will be announced. As I announce quiz 1,
that's what you're
I also
announcing. Okay.
yeah, I also give
Okay.
you a due date.
Okay. All right. Sounds good.
Yep.
Thanks. See ya.
See ya. Have a wonderful weekend.